Hello and welcome to the lecture number 15 of Physics 401A. In this lecture, we discuss the motion under a specific type of central potential which varies as 1 by r or r to the power minus 1. Okay. In addition, we only discuss the attractive type of 1 by r potential here, which simply gives us the famous Kepler problem. As in the previous lecture, we mentioned that only two central potentials where UR varies as 1 by R and where UR varies as R square, they assure all the finite motions to be in closed orbits, right? And that's why these two potentials have special importance in physics. Again, in terms of the practical importances, you can see that all the planetary motions, okay, or the classical model of the motion of the electrons around the nucleus, they are actually falling under the class of UR proportional to 1 by R. And again, the simple harmonic oscillator problem falls in the class of UR proportional to R square. So they also constitute a very important subclass of physical examples. Okay, so that's why both of them are important. Here, for the current interest, we first take the 1 by r type of potential, but we take the attractive one. That's why we define our UR to be is equal to minus alpha by r, where alpha is a positive quantity. So UR is a negative quantity. Okay, r being positive always. So U effective, where U effective is the effective potential energy, is nothing but will be equal to minus alpha by r plus h square by 2mr square, where h is the conserved angular momentum's magnitude, and that is equal to mr square phi dot, as you can remember, and alpha is the constant of proportionality. So this part is negative in nature while this part is positive in nature, right? And this is known as, if you remember, the centrifugal potential energy, right? Let us now study how U effective behaves when the the usual potential law is is minus alpha by r. As you can see, as r tends to 0, the centrifugal term becomes dominant, because then r is very small, and that will be a proper fraction because this is approaching 0 being positive, so this will be a positive proper fraction. So 1 by r square will be much greater than 1 by r. Okay, so the centrifugal term becomes dominant and UF practically behaves as h square by 2mr square and reaches, or rather tends to, positive infinity as r tends to 0. That's exactly what is shown here. Now as r tends to positive infinity, okay, plus infinity, then what is the behavior of U effective? Then of course you can see that the 1 by r square term now dies off much more quickly than alpha by r term. Then U effective tries to reach, okay, 0, but being always negative, and that's the behavior which is shown over here. Okay, the net behavior can be drawn as it is drawn over here by the red color. Okay, so here you can see that U effective basically passes through a minimum, because it starts from a positive, large positive value, and then it reaches, at r tends to infinity, it reaches, or rather it tends to reach U effective is equal to 0, but from the negative side, that simply ascertains or assures a minimum, the existence of a minimum, okay, of the system, which is a stable equilibrium point. Now it is not a stable equilibrium point in the true sense, because this is not the U, but the U effective is minimum in this point. But if you just want to represent the whole motion as a effective one-dimensional motion, then with respect to that representative picture, U effective can be as a the total potential energy, and then this point can be thought as a representative point of stable equilibrium. Okay. But one thing is very clear, that's mathematically sure, that at that point DDR of U effective will be vanishing, 0. And if you use that in the expression of U effective, you simply have alpha by R square minus H square by MR cube will be 0. Okay. That will give you the value of R, which is equal to H square by M alpha. So that this is the value where U effective has its minimum. Okay. And you can actually cross check that at that point du effective dr is 0. And if you calculate now the minimum value of U effective, that will be simply the U effective at R is equal to H square by M alpha. You will see that that will be minus alpha square M by 2H square. Okay. Of course, it is a negative value, right? Now we recall that for an arbitrary central force U of R, phi, that is the angle subtended by the particle at the center, okay, by sweeping its, or by the virtue of sweeping its position vectors with time, the angle swept is given by phi, which will be equal to integration over h dr by r square root over 2m e minus u minus h square by r square plus an integration constant, arbitrary constant of integration. Okay. Then this one is actually discussed in the previous lecture. You can see if you want. Okay. Now for the specific case where u r varies as 1 by r, we have to write u as equal to minus alpha by r, then minus u will be plus alpha by r. Then we can do two things. We just first write that dr by r square as minus of d of 1 by r, and then in this denominator we can write the whole term inside the square root as 2me. Okay, this one will be minus 2mu, so u is minus alpha by r, so this will be plus 2m alpha by r. Now plus 2m alpha by r can also be written as plus 2m by h times h by r. Okay, then we have minus h square by r square, okay, plus the constant. Now just by rewriting using a bit trick, you can see that you can, if you just add and subtract this quantity m square alpha square by h square, you can simply write the whole thing as a form of this 2me plus m square alpha square by h square minus a perfect square, which is the square of m alpha by h minus h by r whole square. Okay. Finally, you can write d of hr as also d of hr minus m alpha by h, because m alpha by h is a constant. Okay. Then we just write, or rather we define a new variable z, which is h by r minus m alpha by h. Okay. And we also define this quantity. Let me use this quantity as a square. We simply write the whole integration as minus integration dz by root over a square minus z square plus a constant of integration. Okay. And as you know, if you just take z is equal to a cos theta, it is nothing but the theta plus the integration constant. Okay. Then you write theta is nothing but the cos inverse of h by r minus m alpha by h over square root 2me plus m square alpha square by h square. Okay. So you can see that we have this one is totally a constant quantity. This one has just an r dependence. Okay. Then you can easily solve this equation just like this. So you can now say that we take the origin of phi, which is, of course you can say this constant as a phi 0, and you can just say this is the origin of phi. So if I just say that for some reason, I don't know what is the reason, or rather I don't want to reveal what the reason is, but I just say that let us calculate phi in such a manner that phi 0 is 0 and that constant basically is 0. So for that case we simply have cos phi will be equal to h by r minus m alpha by h over square root 2me plus m square alpha square by h square. That's exactly what I have written over here, and then basically I multiplied the denominator with cos phi. I have this total thing. Okay. Now we multiply h by m alpha on both sides. Then this will become h square by m alpha 1 by r minus 1, and h by m alpha will be entering inside the square root as h square by m square alpha square, and finally we will have root over 2eh square by m alpha square plus 1, okay, times cos phi. If we define this one as p, small p, and this one as small e, that is not very clear from here, but this one as small e, let me just write this, small e, then finally the total equation becomes p by r is equal to 1, that one will be, come to the other side, e times cos phi. Okay, then we can write r is equal to p by 1 plus e cos phi. This is nothing but the polar equation of a conic section, where p is the semi-latus rectum of the conic section and e is the eccentricity. Okay. So we understand that the trajectory under an attractive 1 by r potential, okay, the trajectory will be a conic section. Okay. Now the question is that it is also known that the conic section can be of different type. It can be an ellipse, it can be a parabola, it can be a hyperbola, whatever. But which one is this case? Can three of this is possible here in this case? Well, we will see that. But one thing is that note that now the question is that we supposed for some reason that arbitrary constant to be equal to 0 over here, right? So note that the origin of phi is set at 0 because we wanted to choose the phi, the phi in such a manner that at phi is equal to 0, r becomes minimum. That's exactly the case. If you exactly was, if you just would have written over here that a phi 0 non-zero, non-zero phi 0, then it would simply have p by 1 plus e cos phi minus phi 0. And then you will have said that cos phi minus phi 0 will be maximum when phi is equal to phi 0, right? Then this cos term will be 1 and r will be minimum because this is the total term is in the denominator. So here I just said that if I make that phi 0 to be 0, I am just saying that my choice says that at phi is equal to 0, my r is a minimum. Okay, that is at phi is equal to 0, the particle is at a perihelion point. Okay, that is the choice. You can take any other phi 0 without losing any generality. Okay. So now remember that our current problem is nothing but a reduced version of a two-particle system which is having mutual intrasystem interaction, and the motion is studied with respect to the CM frame. Finally, we don't have to forget that although we are doing everything in very simple form, that means only one representative particle, in fact effective one-dimensional problem, but finally the problem is nothing but a reduced version of a two-particle system where the two particles are interacting. Okay, and the total motion is studied in the CM frame, right? So the position vectors or whatever we are measuring here, they will be the coordinates in the CM frame, right? So here you can see one thing. If you just if you just go through once again, or if you know already, that's good, in coordinate geometry, that you will understand that this is nothing but the equation of a conic section having one focus at the origin. Okay, so if we are now remembering the original problem where the origin is the CM frame, then basically we can say that we can now translate the whole conclusion for the original system and think that two particles, okay, which are interacting on each other by 1 by r potential, basically trace individually a conic section with one of the foci, that means one of the two foci, okay, at the CM of the system. Okay, and this is nothing but the famous Kepler's first law. And when two of the masses, one is very big, I mean very big or greater than the other, then the center of mass practically lies on the bigger mass, right? And then we can say that the one particle is moving in a conic section, okay, having the other particle at its focus, one of the foci of this. Okay, that is the thing. So you can now draw analogy to Sun Earth system, for example. Okay. Okay. Again, have a look at the orbit equation, which is given as r is equal to p by 1 plus e times cos phi. Okay. This is the equation of a conic section. Now, in the case where E is less than 0, that means the total energy is negative. That's only possible when this negative potential energy dominates the kinetic energy, because the kinetic energy part, both the radial and cross radial part, that means the centrifugal energy part, they are positive definite. So the only way by which the total energy can be negative, where the potential energy is dominating over the kinetic energy terms, the total kinetic energy contribution. Then you can simply say that E is less than 0, and then you can easily also say that 1 plus 2Eh square by m alpha square will be less than 1. Because E is negative, then this term will be negative. So 1 plus some negative term will simply be less than 1. And that is nothing but the eccentricity, rather eccentricity square. Okay, if you just remember, this is eccentricity, so this is the square of the eccentricity. Okay, then now the question is that what is the, so we can easily understand that the eccentricity should be less than 1. What is the lower bound of the eccentricity? We all know that the eccentricity must be positive. Okay, so the eccentricity must be greater than 0. Okay, and that is only possible when this mod value of 2Eh square by m alpha square lies between 0 and 1. Okay, so we see that if the total energy is negative, our eccentricity lies between 0 and 1. And this is the case where the conic section is nothing but an ellipse. An ellipse is a closed conic section. Okay. Now, since here u r varies as 1 by r, we know by Bertrand's theorem that all finite motions have closed orbit. Okay. And also we can say that ellipse is one of them. Okay. So this is one of the examples of the closed orbit possible. Now, using formula of coordinate geometry, we have the semi-major axis of an ellipse given by A will be simply equal to p by p by 1 minus e square. And just replacing the values, substituting the values of p and e defined before, you can say this is nothing but is equal to alpha by 2 times mod of e. Okay, I am writing mod e only simply because a is a length and a must be positive, and alpha is positive by definition, so it should be mod of e always. And the same thing will be here for b. B will be equal to p by root over 1 minus e square. So here you can see a is p by 1 minus e square and b is p by root over 1 minus e square. And that will be equal to, after the substitution of proper values, that will be equal to h by root over 2m mod of e. Okay. Once again, we need the mod value over here so that it should be the square root should be real value. Okay. And also we take the positive value finally because B is a positive length. Okay. Here you can see that A does not depend on H, although A depends on mod E. B similarly depends on mod E, but B does depend on H. Okay. Just think, why is that? Okay. Remember that U effective, now remember what we did in the very beginning, that U effective has its minimum value at R is equal to H square by M alpha. Okay. And the minimum energy is equal to minus M alpha square by 2H square. If you just remember, the U effective at the minimum was minus M alpha square by 2H square, right? And this is also the minimum value of E as well, because U effective plus the kinetic energy will be E, and we can say E is E has the negative, E has a minimum value when the radial term of the kinetic energy just vanishes, and simply then the negative value of the, because when the radial part of the kinetic energy vanishes, in principle that is the minimum value for that kinetic energy component. For the rest, we know what is the minimum value, and we can say that that is the minimum value of U effective, and which will be simply equal to, in that case, the minimum value of the total energy. Okay, just think and tell me why it is consistent to think that when U effective will have its minimum value, okay, then it is consistent or legitimate to think that the kinetic energy or the radial part of the kinetic energy, that is half m a r dot square, vanishes. That is who says that both of them can occur simultaneously? That is the question. Okay. But if it is possible, okay, then you can simply write that in that case the eccentricity E will simply be square root of 1 plus 2h square by m alpha square, and E will be E minimum, which is minus m alpha square by 2h square, and that will be minus 1. So E will be 0. And what is the meaning of E0? That means the ellipse will be reduced to a circle. Okay. Now that means that A is equal to B. Okay. Let us now get back once again to the Lagrangian of a particle under any central potential. So till now we have discussed how to recover the Kepler's first law. Okay. Now we will see how to recover the other laws of Kepler. Okay. So the central potential Lagrangian, the Lagrangian of a particle under any central potential in general can be written in a two-dimensional form just by using the plane polar coordinates as half m r dot square plus r square phi dot square minus u of r. Okay, and which leads to the conservation of del L del phi dot is equal to h, where h is nothing but m r square phi dot, that you all know. Now while changing the position along the trajectory, let's say this red one is the trajectory. Okay, now when the trajectory is when the particle has traversed a distance d of r through the trajectory, okay, then the area of the triangle swept by this this triangle, okay, will simply be given as half r cross dr modulus. That means this is the area of the triangle, half r cross dr magnitude. Okay, then you all know that this is nothing but, so this dr, okay, is almost perpendicular to this triangle because this is differential length. Okay, and this is also equal to r times d phi, so it will be nothing but half r square d phi. That will be the differential area traversed. Okay, now the area swept out per unit time, and which is nothing but the areal velocity or sectorial velocity, which is given by d curly a by dt, will be nothing but half r square d phi dt, or half r square phi dot. Okay. Now you can say that m r square phi dot is a constant, as we all know. Now r square phi dot will also be a constant because mass is a constant in our problem. So the sectorial velocity or areal velocity is a constant. Okay, so we can say under any central potential, remember it does not assume any 1 by r potential form or any specific potential form. It is under any central potential, the particle moves with a constant areal velocity in the plane of motion. And that is Kepler's second law. So Kepler's first law was law only for the 1 by r type of potential, where the second law is valid for any central potential. Remember that. That's important. Now the sectorial or areal velocity can be written as a dot, which is equal to dA dt is equal to half r square phi dot, which is nothing but h by 2m. So then you can easily integrate, and you can say, as this is a constant, then you can simply integrate just by saying a is equal to h by 2m times t. Okay. Then t is, t. So where a is the area swept in a total orbit, in a complete orbit. Okay. And t is the time period of revolution for that complete orbit. The area, calculation of the area is possible when we are talking about a closed orbit, right? Then you can say that this is, here we are just talking about the closed orbit, and for an ellipse, this area is nothing but pi times semi-major axis times semi-minor axis, pi AB, right? And t is 2m by h times a. From this definition you can easily write this, and then you can write a is pi ab, so pi will be over here and a will be alpha by 2 mod of e. If you remember over here, I just derived this. A is equal to alpha by 2 mod e, and b is equal to h by root over 2m mod e. Okay, if you replace those two values over here, finally you will see that t will be equal to 2 pi root over m by alpha. There are two forms. One is pi alpha root over m by 2 mod e to the power minus 3 by 2. Another equivalent form is 2 pi root over m by alpha a to the power 3 by 2. And from that you can simply write that t square will be proportional to a cube, right? So that means that the square of the time period will be proportional to the cube of the semi-major axis of the closed orbit, or the ellipse, okay, traced out by the particle, okay, by the moving particle. That is nothing but Kepler's third law. Okay. Now you try to think, we have discussed this one for an attractive 1 by r potential given the total energy is negative. Now try to think the orbit and the corresponding conditions, okay, for E greater than 0 and E is equal to 0. E is equal to 0 means the kinetic energy will be exactly balanced. I mean the total kinetic energy. That means in our language, that means the radial kinetic energy plus the centrifugal potential energy or the cross radial kinetic energy will be exactly balanced by the minus alpha by r term. Okay. So just think and check over internet, or you can ask me as well. Okay. Till now we have discussed the orbits. That's very good. But and also their nature and properties, and also we recovered three we have rediscovered, or rather reobtained 3 laws of Kepler, okay, which you have already learned, okay, before. But as you can remember that our main objective was to find r as a function of t. That is the main objective of solving all the equations of motion, right? Then let us recall the formula. T is equal to integration dr over square root 2m e minus u minus h square by m square r square plus a constant of integration. Okay. Now for the current situation, we consider elliptical orbits where a is equal to alpha by 2 mod e and e, small e, that is the eccentricity, is root over 1 plus 2 capital E h square by m alpha square. Okay. Then you can simply write that t is equal to root over m by 2 mod e integration dr over square root minus 1 plus alpha by r mod e minus h square by 2r square m mod e plus the constant of integration. Remember, when you take this mod e, or rather square root of mod e, common, or rather outside the integration, just remember that here in our case e less than 0, right? E is less than 0. We are just discussing that the case where e is less than 0. That's why our mod e will simply be equal to minus of e, and that's why here this minus sign comes. Okay. Then again you can write that this one is equal to root over m by 2 mod e integration r dr. I am just multiplying r in both the numerators and the denominator. So r dr root over minus r square plus alpha r by mod e minus h square by 2m mod e. Okay. Now you have to do something very tricky, that you have to now substitute the values of a and small e, that is eccentricity, accordingly in this fraction, and that's a small homework to you. Okay. You can easily do that. This is not a very big task, just 2-3 lines of algebra, and you will see that this equation just gets reduced to root over m a by alpha, okay, integration r dr over square root a square small e square minus r minus a whole square plus the constant. Okay. Now you do a change of variables just by redefining a variable xi by saying r minus a now be defined as equal to minus a times small e cos xi. Then you can write the whole thing, if you remember the whole thing, okay, is as root over m a cube by alpha integration 1 minus e cos xi d xi plus the same constant of integration will be appearing here. Okay, so I will give you that as a small tutorial problem as well, that to come from here to here and then from here to here. Okay, so if you do that, you will finally see a form which is very easily integrable, and that is nothing but the integration is xi minus e sin xi plus the constant of integration. Okay, so if we say now that the time is measured in such a way that c is made to be 0, then we have the parametric relation between r and t. So r will simply be a times 1 minus e cos xi. That is possible, that is easy to see because from this definition of this new variable. So r will simply be a minus a e cos xi, so a times 1 minus e cos xi, and t will be equal to this one, root over m a cube by alpha times xi minus e sin xi. Okay, so by solving those two, one can look for the trajectory, okay, from trajectory under this type of attractive potential and negative energy. The total energy is negative. Okay, now my question to you is that where should the particle be basically in terms of r at t is equal to 0? And can you also do similar analysis for the orbits with E greater than or equal to 0? I have done only for E less than 0. Okay, that's you to do. Okay, now all these things we have done, we're just using attractive potential. That's why we came across Kepler's problem. Now, if the field is repulsive, that is U of R is equal to alpha by R, okay, where alpha greater than 0, so it is a positive quantity, then what happens? Can we apply all the tricks and all the formalisms to that case as well? One thing is sure, then the total energy will be E is equal to half m r dot square plus alpha by r plus h square by 2m r square. And one thing is also true, that there will be no case where E will be less than 0, right? So now you tell me which type of trajectories are possible, which type of conditions will be there, which type of orbits will be possible. Okay, so this type of analysis, you have to do. Okay, that's good to do. Similar type of analysis can be done, of course, for that. That's the good news. And this type of field is also interesting. That means where U is repulsive in nature. Also interesting because it clearly represents a very interesting phenomena. Okay, which is, or rather, actually a practical or experimental evidence of nucleus. Okay, and that was done first time by scientist Rutherford, and this is known as the famous experiment of alpha scattering. Okay, so you just try to apply all the formalisms to analyze the orbits and the trajectories and the corresponding, corresponding conclusions, that where the particle B at t is equal to 0, at the phi is equal to 0, this type of small conclusion as well. Okay, for this repulsive case. Okay, and you can also see this in a standard textbook as well. Okay, thank you very much.